I am Ijaz Ahmed. In this lecture, we will discuss about the group actions and then proceed towards proving the orbit stabilizer theorem with some applications. So we start by the definition. Group action. So how do we define group action? A group action of a group G a group action of a group G on a set A. On a set A is a mapping from G cross A to A. And this is usually denoted by G dot A for all G in G and A in A, satisfying the following properties. Satisfying the following properties. So a group action is a mapping from G cross A into A. This is denoted by G dot A, where G belongs to G and A belongs to A. And then this mapping must satisfy the following properties. The first property is G1, G2A must be equal to G1, G2 of A for all G1, G2 belonging to G and A belonging to A. And it should also satisfy the second property, like 1 dot A should always be equal to A for all A belonging to A, where 1 is the identity of G. Then once we have a group G and a set A and a mapping from G cross A into A satisfying these two properties, then that mapping will be called a group action of the group G on the set A. For example, uh, let's choose the group D3. So let the group G is the dihedral group of an equilateral triangle, and let A be the set containing three elements 1, 2, 3. Then there is a group action defined from D3 cross A into A by suppose let us choose some D from D3 and some I from the set A, and this is equal to suppose D of I, something like that. Then this kind of a mapping satisfies these two axioms and hence defined as the group action. So we can take, for example, suppose if the elements of D3 are like R0, R120, R240. So these are the three rotations: the rotation of 0 degree, rotation of 120 degree, and rotation of 240 degree. And let's name the vertices of the equilateral triangle on which the group D3 has been defined as 1, 2, 3. So suppose the three vertices are 1, 2, 3. Then it is, let's name them as V1, V2, and V3. Then this is the reflection that keeps the vertex V1 fixed and moves the other two vertices. Then this is the reflection along the vertex V2, and this is the reflection along the vertex V3. So these are the six elements of D3. Then these elements act on the set 1, 2, 3. And in fact, in the previous lecture, we had already seen that every group action actually defines a permutation on a set A. So how these elements now define a permutations on the set A, we shall do it something like here. Now since R0 is the identity element, so R0 will keep everything fixed. So the first thing is R0 all elements, fixes all elements in A. So this implies R0 gives rise to an identity permutation. Gives rise to an identity permutation on A. So therefore R0 gives rise to an identity permutation. Now let's look at what R120 does. So now R120 of I. Now since I belongs to the set A, so I is equal to 1, 2 or 3. So we shall define all the things separately. Now suppose our equilateral triangle on which the set D3 has been defined. Let's make that triangle here. So it is like this. This is 1. This is suppose vertex. Let's name this as vertex V1. This is the vertex V2. And this is the vertex V3. Now R120 of I. Now R120 of I is a 120-degree rotation of this. This is, let's assume this to be the identity figure. Then rotation of 120 will send V1 into V2, it will send V2 into V3, and it will send V3 into V1. So 1 R120I. So under this, this will give rise to a permutation which sends V1 into V2, it sends V2 into V3, and this R120 sends V3 into V1. So it is V3 into V1. Now this will act on the elements I. So on 1, the image of 1 under this mapping is 2, and the image of 2 under this rotation is 3, and the image of 3 and this 3 will be sent to 1 under this rotation R120. So actually the permutation that is arises from the rotation 120 is the permutation 1, 2, 3. Now similarly, let's take the example as what these elements reflection. Similarly, we can see the rotation of 240 degree will give rise to a permutation 132 on the set A, which contains elements 1, 2, 3. Now let's look at how these reflections give rise to the permutation. So it is, suppose let's choose FV1 of I. Now FV1 is the reflection that keeps the vertex V1 fixed and reflects these two vertices V2 and V3. So under the reflection FV1, this can be written in a permutation form like, so V1 keeps fixed, so V1 goes into V1, and now V2 and V3 are interchanged under this reflection, so V2 will go into V3 and V3 will go into V2. Now this permutation will do something to the elements of I. So under this permutation, the element 1 goes into 1, 2 goes into 3, and 3 goes into 2. So this is the permutation 2, 3, and 1 remains fixed. So therefore, in this way, we can see that this reflection FP1 gives rise to a permutation on the set A equal to 1, 2, 3, and that permutation has this nature, which fixes 1 and interchanges the elements 2 and 3. So this is how we define the group action. For example, we can take one more example. The group, suppose the set of the group of integers acts on itself by, suppose some zx is equal to z plus x. Then this mapping defines a group action of the group Z acting on itself. Now similarly, the permutation group. The permutation group, suppose SA. So this is a permutation group defined on the set A, acts on A by, suppose, sigma of A is equal to sigma of A. So this is the mapping that we will define from SA cross A into A. So the sigma is a mapping, actually this sigma is a mapping from SA cross A into A, defined by this way. The sigma of A is equal to sigma dot A is equal to sigma of A. Then this mapping will define a group action of the group symmetric group SA defined on the set A. So therefore the symmetric group SA acts on the set A. Now we move to one more definition, definition number 2, that is stabilizer. Stabilizer of a point. So let G be a group acting on the set A, acting on the set A, and let A be a point in A. Then we define the stabilizer of A. Then the stabilizer of A belonging to A is the set which is usually denoted by GA, and this is the set of elements of G. This is G belongs to G, such that G dot A is equal to A. So by the term stabilizer, the stabilizer of the point A, as the name stabilizer suggests, it is a set of those elements of G which stabilize the point A, which actually fix the point A. For example, as seen in the previous example, we had taken the group G as the group D3 and A the set with three elements 1, 2, 3. Then uh, let's try to find what is the stabilizer of point 1. Then stabilizer of point 1, that we shall denote by G1, is the set of elements G belonging to D3 such that G of 1 is equal to 1. So it's actually those elements of D3 which fix the point 1 from A. So in fact we can see here that the identity rotation, the identity element of D3 will in fact fix everything. So it will in particular fix 1. And now here we can see that R120 does not fix 1, and similarly we can easily verify that R240 will not fix 1. So therefore R120 and R240 do not belong to the stabilizer of 1, but in fact R0 belongs to the stabilizer of 1. Now we can look at FV1, and this mapping here we can see that this element of D3 fixes 1. So therefore FV1 also belongs to a stabilizer of 1. Then we can easily verify that FV2, it will not stabilize 1, but it will stabilize 2 from the set A which contains 1, 2, 3. And similarly FV3 will stabilize 3, and therefore it means that the stabilizer of G1. So it means that G1 is containing the two elements R0, the identity rotation, and the reflection along the vertex V1 of the equilateral triangle that contains its vertices as V1, V2, and V3. And similarly, the stabilizer of 2, that's denoted by G2, it is again the set of points in D3 such that G of 2 is equal to 2. Now, keeping the same things in mind, we can see that the identity permutation, the identity reflection fixes everything. So it in particular fixes the point 2, and in fact the reflection along the vertex V2 will fix the point 2. So therefore the stabilizer of 2 will be the point, will be the set R0 and FV2. Or sometimes the stabilizer is also denoted by the stabilizer of A. So therefore here we can write this is the stabilizer of 1 and this is the stabilizer of point 2. And similarly we can also define the stabilizer of 3 from the set E. Now we prove one result here. So let's make it as a theorem, or in fact it is a very simple result, but it is important result here. Uh, the stabilizer, suppose GA of a point A belonging to A is a subgroup of G. So in fact here we are actually taking that there is a group G and there is a set A, and the group G acts on the set A. Then the stabilizer of every point of A actually defines a subgroup of G. So let's proceed towards proving this result. So before choosing something from the stabilizer of A, we must be knowing that the stabilizer of every point is actually a non-empty set. So let us define the stabilizer of A here. So stabilizer of A is the set of points G belonging to G such that G stabilizes A, or as seen in the previous lines, this is also denoted by stab of A. So first clearly, stabilizer of A is not equal to 5 because the identity element 1 belongs to the stabilizer of A. The identity element always fixes everything, so therefore the stabilizer of any point is always a non-empty set. Now let G comma H belong to the stabilizer of A. So this implies this implies G dot A is equal to A and H dot A is equal to A. Now here in both of these cases, G is an element from G, the group, and H is also an element from the group. So therefore, from the group G, both G and H will have the inverse. So this implies that from the second equation, A can be written as H inverse of A. So that is H inverse dot A is equals A. So once we have an element from G that stabilizes A, the inverse of that element from G also stabilizes A. So actually what does this mean? This means that H inverse belongs to stabilizer of A. So in fact we can also see that G inverse also belongs to the stabilizer of A, but we are in a process of proving that stabilizer of A is a subgroup. So actually we need to show that GH inverse must belong to the stabilizer of A. So now let's see what GH inverse does to the point A. Now GH inverse of A. Now by the definition of GH inverse of A and by the definition of the group actions, since this is defined as a group action, so this by definition is G H inverse of A. This is by the first axiom of the group action. So this is equal to G. Now since H inverse of A is equal to A, so this is equal to G of A. And now since G also stabilizes A, and so this is equal to A. So this means that G H inverse belongs to the stabilizer of A. So therefore stabilizer of A is a subgroup of G. A subgroup of G for every A belonging to A. Now let's proceed towards, before doing one more definition, we shall take one more example of a group action. So for example, let G be the group of integers under addition, in fact, and let A be the set Z4. That is the set of integers modulo 4. So in fact, A also forms a group, but here we will just treat this A to be a set and let G be a group. Then G acts on A. G acts on A by G dot A is equal to G plus A, and in fact mod 4, because the Z4 is a set modulo 4. Then this is the group action of G on the set A. We shall here compute the stabilizer of all the points of A. Then the stabilizer of 0, the stabilizer of 0 is the set G belonging to Z such that G dot A is equal to A. So actually G of 0 is equal to 0, G dot 0 is equal to 0, which is actually, since this Z is a group under addition, so it's actually G belonging to the group of integers Z such that G plus 0 is equal to 0. So in fact, we can see here that this 0 plus 0 is equal to 0, so 0 belongs to here. And in fact, in the set Z4, 4 plus 0 is again equal to 0, and minus 4 plus 0 is again equal to 0. So it's plus minus 4, and similarly it is plus minus 8, and similarly all the multiples of 4, plus minus 12, and so on. And this can be seen, this is actually the set 4Z. So therefore stabilizer of 0 is this 4Z. And similarly we can look at the stabilizer of 1. It is G belonging to Z such that G dot 1 is equal to 1, but by the group G, which is the group under addition, this can be written as G belonging to Z such that G plus 1, this should be equal to 1. So in fact, we can see here that 0 does not belong to this set. So this is the, in fact, 0 belongs to the set because 0 plus 1 is equal to 1. So this contains the 0. And in fact, this contains 5 now, because 5 plus 1 is equal to 5. But 5 in Z4 means 1. So this contains plus minus 5, and similarly plus minus 9, then plus minus 13, and so on. So actually this is the subset of Z, which is 4n plus 1 into Z. So the stabilizer of G0 was 4Z, and the stabilizer of Gn is 4n plus 1 into Z. Similarly, we can see that the stabilizer of G2 is equal to 4n plus 2Z, and stabilizer of 3, which is an element of Z4, it is equal to 4n plus 3Z. Now here we can clearly see that all these are actually this G0, G1, G2, and G3. They are all the subgroups of Z. Now we make one more definition here, that is the kernel of a group action. kernel of a group action. So the kernel of a group action of group G on A is the set. So this is actually the set of elements of G such that G dot A is equal to A for all A belonging to A. So it is a set of those elements of A that fix every element of A. So for example, let us take the group G, the set of integers, the group of integers Z, and let A be the set Z4. Then the kernel, then kernel of, then in fact then the group action is, then the group action is, then the group action is defined as, is defined as Z of A is equal to Z plus A, where Z belongs to the group Z and A belongs to the set A. Then we shall try to see what is the kernel. So actually kernel is the set of those elements of G that fix every element of A. So let suppose G belongs to the kernel. Then this G must fix all the elements of Z4. Then we must have G plus 0 is equal to 0. We must have G plus 1 is equal to 1. And we must have G plus 2 is equal to 2. And we must have G plus 3 is equal to 3. Now we have to verify that what are the elements of this Z which satisfy all these four equations. So in fact we can see that it is actually the multiples of 4 that satisfy all the four equations, since we can see that 0 satisfies all of these equations, 4 satisfies all of these equations, minus 4 satisfies all of these equations. In fact every multiple of 4 satisfies all of these equations. This clearly implies that G is equal to plus minus 4. In fact plus minus 4n. So therefore so this implies kernel of action of G, sorry, kernel of action of Z on Z4 is 4Z. And in fact, we also have a result here. This is a small result here. Let's name it as a theorem. The kernel of an action defines a subgroup. Now we move towards one more definition, because we are actually proceeding towards proving the orbit stabilizer theorem. So we move towards the definition of orbit of a point. orbit of a point. Let G be a group. Let G be a group acting on the set A. Acting on the set A. Then the orbit of point A belonging to A is the set. It is usually denoted by orbit of A, and this is the set G of A such that G belonging to G. So it is actually the action that is made by G on this fixed point A. So actually here we have to compute the images of A whenever G belongs to G. For all G belonging to G, we have to compute G of A, and that set will define the orbit of a point A. For example, let G is equal to D3, and suppose A is the set 1, 2, 3. Then we have a group action. Then let us compute the orbit of 1. Then orbit of 1 is equal to D1 such that D belongs to D3. Now there are 6 elements in D3, and we have to see what are the images of, what are the actions of the elements of D3 on this fixed point 1. So first the identity mapping. Identity element of D3, that is R0, the rotation of 0 degree, it fixes 1. So under R0 it is actually R01, then it is R121, then it is R241, this is by the definition, then this is FV1 of 1, then FV2 of 1, and it is FV3 of 1. Now R0 fixes 1, so it is 1, and R120, it moves 1 into 2, so it is 2 here. Now R240, it moves R it moves 1 into 3. Now FV1, it fixes 1, so 1 is already appearing here. Now FV2, it fixes 2 and moves 1 into 2. This moves 1 into 3, but 3 is also already here. And FV3, this also moves 1 into 2, but 2 is already here. So this is the orbit of 1 under the group action of group D3 on the set A containing these 3 elements 1, 2, 3. So now as we have done the stabilizer and we already know what is orbit of a point, now we can proceed towards defining the orbit stabilizer theorem. So we have now this orbit stabilizer theorem. So what is orbit stabilizer theorem? Let G be a finite group of permutations. G be a finite group acting on a set A. Then for any A belonging to A, the order of G is equal to order of stabilizer of I, stabilizer of A, and order of orbit of A. So, and we also have made one more notation for the stabilizer of A. So this is actually order of G into into the order of orbit of A. And this holds for every point of A. So if we choose any point of A and then compute the orbit of A and the stabilizer of A, then the product of the orbits of, then the product of the orders of these two sets for every fixed point of A actually gives the order of the group G. So this is the orbit stabilizer theorem. So it is the use of orbit and the stabilizer for uh, finding out the order of a given finite group G. Before going into the proof of this theorem, we shall look at the order of D3 by using the orbit stabilizer theorem. So let us take one example first, then we will go into the proof. Example, since we have already seen that if suppose our group G is equal to D3 and the set A is the set 1, 2, 3, then we choose some let's 1, then 1 belongs to A. Then the stabilizer of 1. Stabilizer of 1, as it was computed earlier, it is the two elements from D3. One was R0 and another was FV1. And in fact, previously we defined here the orbit of 1. Orbit of 1. It was containing three elements from the set A, that is 1, 2, 3. So therefore order of stabilizer of 1. Order of stabilizer of 1, this is equal to 2, and order of orbit of 1, that is equal to 3. So this implies orbit of G by the orbit stabilizer theorem. This should be equal to order of G1 into order of orbit of 1. And now order of G1 is equal to 2 and order of orbit of 1 is equal to 3, and so this is equal to 6. And we already know that D3 is a group that contains 6 elements. So therefore we have found out the order of D3 by the orbit stabilizer theorem here. Now we will go into the proof of the orbit stabilizer theorem, and then we will take one more example of a group to find out the order of that group by the orbit stabilizer theorem. So let's go into the proof. So actually first we will first introduce the idea as how we will proceed towards proving this result. So the main idea behind proving the result will be like, we will define a mapping from G upon stabilizer of a point A into the orbit of A. We will try to define a mapping from this. Actually, this left-hand side defines the set of all left cosets of the stabilizer of A in the group G, and this is the orbit of A, and we will define a mapping from between these two sets and prove that the mapping is 1, 1 and on 2. And that will imply to us, once we have a 1, 1 on 2 mapping between these two sets, and since G is a finite group as it is given in the statement, therefore these two sets will have the same order. So once they have the same order, we will obtain order of G by order of G of A is equal to orbit of stabilizer of A, and that will imply to us that order of G is equal to orbit of A into orbit of stabilizer of A. So this will be the main idea behind proving this result. So we know that it is actually by Lagrange's theorem. By Lagrange's theorem, order of G upon order of stabilizer of A is the number of distinct left cosets of stabilizer of A and G. So in order to prove our result, we establish a bijection between G upon stabilizer of A to orbit of A. So now let's define this map. So let T be a mapping from G upon stabilizer of A into orbit of A. So in fact here we are not treating the stabilizer of A to be a normal subgroup, we are just defining the left cosets here by suppose T of, now every left coset of G upon stabilizer of A will be of the form, suppose G stab of A, and this shall be defined as G of A. Now we prove that this mapping is a well-defined mapping and is also 1, 1 and only. Now to show T is well defined. For showing this, let T of suppose G stab of A is equal to T of H so actually we have to take two elements from G upon stab of A for proving the mapping to be well defined. We have to choose two elements from this G upon stab of A. Let G stab of A and H stab of A be two elements from G upon stab of A such that G stab of A is equal to H stab of A. So that means we are taking the elements G stab of A and H stab of A from G upon stab of A and assume them to be identical elements, and by the definition of the cosets, since these are the elements from the cosets and by since these are the two cosets actually, so by the definition of the cosets, either two cosets are equal or they are identical or they are completely disjoint. So when G stab of A is equal to H stab of A, and by definition this means that this GH inverse belongs to the stab of A. So once we have two identical cosets, it means that GH inverse must belong to the stab of A. So once we have something from the stab of A, it must fix the element A. So by definition, when we have GH inverse is an element of stab of A, we must have GH inverse of A is equal to A. So this implies, or even we can here write not necessarily GH inverse, or we can even write uh, G inverse of H. So it's one and the same thing actually. Remultiplying by G inverse here, this gives G inverse of H belongs to the step of A, because that is what helps us here. So it is G inverse of H is equal to A. So this gives us H of A is equal to G of A. But by definition, this implies, by the definition of the mapping, this implies G step of A, this implies T of G step of A is equal to T of H step of A. So therefore, this is a well-defined mapping. Now we can reverse the arguments here and show that the mapping T is also 1, 1. Now reversing the arguments here, we can show that T is 1. Now the last thing that needs to be proved is that T is onto. Now let J belongs to the orbit of I. Suppose let's choose B. Now let B belongs to the orbit of A. So once we have some element from the orbit of A, it means that there is some element from the group G. So this means there is G belonging to G such that G of A is equal to B. So thus, but we need to find something from T upon step of A, whose image is this B. So thus there is T of G step of A, then by definition this is equal to G of A and this is equal to B. So therefore for every element B in the orbit of A, there is G step of A in G upon step of A such that G of step of A is equal to B. So therefore this means that the mapping is an onto mapping. So therefore T is a bijection from G upon step of A into orbit of A. So therefore, thus order of G upon order of stabilizer of A, this is equal to order of orbit of A. So this gives us order of G is equal to order of stabilizer of A into order of orbit of A. So this proves the orbit stabilizer theorem. Now we will take one more example of a group and compute its order using the orbit stabilizer theorem. The group of rotations of a cube. The group of rotations of a cube. We will use the orbit stabilizer theorem to see what is the order of the group of rotations of a cube. Suppose here we assume that the sides of the cube are named as 1, 2, 3, 4, 5, and 6. Let's assume our cube is like this. So let's try to construct a cube here. Okay, so let's have this as our cube. Let this face be named as 1, and the face in the bottom be named as 6, suppose. So this 6, and the faces which are actually here in the vertical position be named as 2. So let's name this face as the face at the back side, let's name that as 2. This is the face on the right side here, let's name this face as 3. The front face be named as suppose 4, and the face on this left hand side suppose be named as 5. Then we will choose an element, then we will choose one of the faces here which shall be treated as the elements of the set A, and the set A will have here 6 elements, and then we will compute the orbit of that face, and we will also compute the stabilizer of that face. Then use the orbit stabilizer theorem to compute the order of the group of rotations of a cube. So let's choose face C1. Then stabilizer of 1. We will just look at the order of the stabilizer of 1. So order of the stabilizer of 1 will be those rotations of the cube that keep the element 1 fixed. And those rotations should be can be looked like we will rotate the cube along the axis through the face 1 and perpendicular to the other faces, to the other 4 faces like 2, 3, 4, and 5. So we will rotate this cube horizontally along the axis which is perpendicular to the faces 1 and 6 and passing through the center of the faces 1 and 6. Then there will be 4 90-degree rotations which will keep the faces 1 and 6 in fact fixed, but here we just need those rotations which will keep the face 1 fixed. So there are 4 rotations of 90 degrees which will keep the element 1 fixed, and those rotations can be taken as by rotating this cube horizontally along the axis which passes through the center of 1 and is perpendicular to the face 1. So therefore in this way we can see that the order of the stabilizer of 1 is equal to 4. Now let's see what is the order of the orbit of 1. Now under rotation we can make a 90-degree rotation towards the right hand side like this, and this one will be moved into the point 2. Then we can also make a 180-degree rotation clockwise in the clockwise direction, and we can see that one can be moved into the face 6. So one can be moved into 2, one can also be moved into 6. And similarly, if we similarly make, in fact we can make the rotations either horizontally or vertically, and we can see that, we can visualize that one can be kept fixed by making no rotation, making a 0-degree rotation, and one can be moved into any other phase by some rotation. So therefore it means that the order of orbit of 1 will be equal to 6. So thus order of G in this case will be equal to 4 into 6, and that is equal to 24. So this means that the order of the group of rotations of a cube is equal to 24. So with this thing we stop this lecture.